Alright, here is the magnetism review video. I'm going to be a little bit faster than Mr. Tarshis is, just because I want to get this done as quickly as possible. Magnetism. So we're dealing with magnets and magnetic fields. Let's start off with permanent magnet. Permanent magnets are any things that have a north and south pole, and they are dipoles. Every magnet has a north and south pole, and only magnetic dipoles exist, where di means two. Even if you break a magnet in half, you can't ever get just a north or just a south, as far as we know. It wouldn't ruin physics if we found one, but as far as we know, they don't exist. Opposite poles attract, like poles repel, pretty simple. And magnetic fields are always closed loops, so they begin and end somewhere, pointing from north to south. Now it looks in this picture like they're not closed loops. The idea is that these over here trail off to infinity, and these come back from infinity, so they loop around at infinity. Also, the Earth's magnetic poles, the Earth is a giant magnet, and the Earth's magnetic poles are opposite the geographic poles. So at what we call the North Pole is the south end of the Earth's magnet. At what we call the South Pole is the north end of the Earth's magnet. First question. Two bar magnets should be cut in half along the dotted line shown. None of the pieces are rotated. So we cut them, then leave them just like they are. After the cut, what will happen? So my first step is to write down what the cut will look like. So if this is the north side of a magnet right here, we cut it, we'll get a south, a north. On this bottom one, we'll get north, south, north, south. So if we leave them just like that, the question is what will happen. So it looks to me like these two will attract. You got north and north next to each other, they'll repel. So let's look through the answers. None of the halves will attract, no. The two halves will attract, no. The two halves will both repel, no. Two halves of the top will repel, nope. Two halves of the top will attract, two halves of the bottom will repel. Yep, that's what I said. A charge moving through a magnetic field will experience a force unless the charge is stationary, or you gotta have QV cross B. If you put in a 0 for V, done. Charge is moving parallel to the magnetic field. This cross part, where we do the right-hand rule, if you have V and V parallel to each other, so if velocity is like that, and magnetic field is like that, no force. They can't be parallel. Velocity and magnetic field can't be parallel and still get a force. Alright, you know the right-hand rule. This one shown here is the one I showed you, I think, first, then I showed you the one with the 2 fingers. People seem to like that, or 3 fingers if you count your thumb. People seem to like that better just because it's harder to mess up. Alright, so electric charges will get forced by a magnetic field if they are moving perpendicular, hence the perpendicular part of the right-hand rule. A positive charge will follow the right-hand rule. A negative charge you flip over, or you can use your left hand. It's pretty dangerous to use your left hand. I think that's easier to mess up because you might forget which one you're dealing with. If you got a positive charge, it does what the right-hand rule says. If you got a negative charge, you just flip your right hand over when you're done. The equation, once you've done the right-hand rule for getting the force, is charge times velocity times magnetic field. Force is measured in Newton, charge in coulombs, velocity in meters per second, magnetic field in Teslas. The magnetic force, whenever you have a charge going through a magnetic field, that charge will start to move in a circle, unless, of course, the initial velocity was parallel to the field, but the charge will start to move in a circle. So the magnetic force will serve as the centripetal force, and so you can set QVB equal to mv squared over r. Remember that mv squared over r is centripetal force. And magnetic force does not do any work because it's always perpendicular to the velocity. So if you think about your right-hand rule up here, your force is always at a right angle to your velocity. And from what we know about work, if your force and your displacement are at right angles, you have no work done. Alright, I really like this next question because it's one of the things people tend to mess up. A positively charged particle moves to the right. It enters a region of space where there is an electric field directed up the plane of the paper as shown. In which direction does the magnetic field have to point in this region so that the particle maintains a constant velocity? Well, if the particle maintains a constant velocity, that would be translational equilibrium, meaning that up forces equal down forces, left equal right. So up here, our particle in the field, if this is an electric field, and this is a proton, so it's a positive particle, or it doesn't have to be a proton to be positive. If this is a positive particle, it will experience a force upward from the electric field. And if we want to create equilibrium, we will need a magnetic force downward. So our magnetic force will need to be down. I'll use the right hand rule, put my thumb down. I know the velocity of the particle is toward the right. And when I use my right hand in the shape of the right hand rule, I get that magnetic field to create a magnetic force down. The magnetic field would have to be out of the page. So the magnetic field will look like that. And that is answer choice B. The key here, and the thing people mess up a lot, is just because the magnetic force is down doesn't mean the magnetic field is down. You're trying to balance the forces, not the fields. Remember, you're not trying to balance fields. Don't ever do that. Balance forces, and then figure out what the fields look like. Also, I'll throw in here, if this were a negative charge, our electric force would have had to have been down, and then we would have had to have a magnetic force up, so we'd have to manipulate our right-hand rule thusly. A straight wire carrying a current, because it's just a collection of electric charges moving along, is forced by a magnetic field perpendicular to it. We use conventional current, which means we pretend like the protons are the things moving. And so we'll use the current as our velocity in the right-hand rule. The electron flow is actually flowing in the opposite direction. So if your question told you which way the electrons went, you could use the opposite of the right-hand rule, or use your left hand. The formula for force on a wire in a magnetic field is F equals ILB, where force is in newtons, I is current in amperes, L is the length of the wire in meters, and B is the magnetic field in teslas. If you have a loop of wire in a magnetic field, use the right-hand rule, number 1, for the force on each section of the wire. So if we look down here at this problem, notice we have a loop of wire. What we do is we check every section of the wire, every side of that shape. Certain things can happen to the loop. The loop can get stretched outward, so the forces could apply outward and stretch the loop. The forces could apply inward, make the loop smaller, or rotate the loop, torque, which is what this next question is about. You're also getting some torque review. How about that? So here's our question. A square loop of wire, 0.3 meters on a side, carries a current of 2 amperes and is located in a uniform 0.05 Tesla magnetic field. The left side of the loop is aligned along and attached to a fixed axis. So this is like a door. Your loop here is like a door, and this is the axis that the door swings on. When the plane of the loop is parallel to the magnetic field in the position shown, what is the magnitude of the torque exerted on the loop about the axis? So I'm going to work this problem backwards, which has always been my advice to you. First, I'm going to start with, I am going to end up with a torque. And a torque is a force times the radial distance applied that force is applied. So the distance from the axis of rotation. R is the distance from the axis of rotation. Now I need to think about, well, what are the forces? If we scroll back up a bit, you just found out, using the right-hand rule number 1, this point here, you can get a force on each section of the wire. So that means I'll get a force on the top side, the right side, the bottom side, the left side. And that's for a wire loop. So this loop will get a force on every side. So let's figure out what those forces are. I'm going to start with the top, right here. So I am first going to be curious about, well, what's the direction of the force, the magnetic field? So let's do V is to the right with the current. The magnetic field is to the right. I cannot do a cross product there. Both fingers are pointing to the right. Those are not perpendicular. They're parallel. If you've got velocity parallel to the magnetic field, no force. So up on this top part, F equals 0. So I don't have to worry about it. Now let's do the right side. The right side, I've got my velocity down along with the current. I've got my field to the right, magnetic field to the right. My thumb points out of the page. So my force, magnetic force, is out of the page. And from up above, I can get that force from the equation F equals ILB. So that force will be F equals ILB. Come back to that later, though. I'm going to plug in the numbers when I'm done. All right, now let's look at the bottom section. So I have velocity to the left, magnetic field to the right, and my fingers won't do that. Those are not perpendicular, they're parallel, or more specifically anti-parallels, because they're in the exact opposite directions. But no force, because you've got your field and your velocity parallel. So on the bottom here, force is 0. Alright, now the left side. I've got my velocity up, my magnetic field to the right, and I get force into the page. So over here on the right, my magnetic force seems to be into the page. It's an X into the page. FB into the page. Okay, so I've got two torques, exactly. I've got one on the left side and one on the right side. So I'll do torque on the left side and torque on the right side. And since the problem is asking me what's the magnitude of the torque exerted in the loop, when I'm done, I can just add the two torques together. So I'll do torque left plus torque right. I'm not trying to balance them, not trying to make this thing have no torque. I'm just trying to see what the total torque is. Torque on the left. So the magnetic force is given by FB equals ILB. So I can put that in for the force part in torque. I should write my equations. So this will be force on the left side times radius from the axis on the left side plus force on the right side times radius on the right side. Alright, so I'll sub in what my forces are. That would be, keep color coding, ILB. And then my radius, I notice that if it's the distance from the axis, well, the axis is right there on that side of the loop. So the distance from the axis, that radius is 0, making this entire side 0. So I'm done worrying about that. Notice this problem seemed intimidating at first, but slowly got easier. Lots of things turned out to be 0. It's a trick that happens often on the AP exam. So now on this side, I'll do ILB for my force, and my radius, my distance from that axis, 0.3 meters. 0.3 meters. And I just look up at the top and notice that from the axis to the right side is 0.3 meters. So now ILB, let's plug those in. I'll get 2 amperes times 0.3 meters times 0.05 Teslas times 0.3 meters. Okay? So you don't get a calculator on the multiple choice part, but I'm going to notice that there are some things I can mix together here. I'm going to take the 0.3 and the 0.3, multiply those together, and get 0.09 meters squared. I'll do 0.05 Teslas times 2 amps and get 0.1 Tesla amps, whatever the hell that is. And when I multiply those two things together, I'll get my torque of 0.009 Newton meters. And looky there, answer choice B. Next, we move on to the right-hand rule for a current-carrying wire. The magnetic field of a straight wire forms a closed circular loop around the wire. So your magnetic field will always make this circular path around the wire. What you do is you point your thumb in the direction of current and your fingers curl in the direction of the magnetic field. If you're using electrons, so if instead of giving us current, this problem gave us the direction of the electrons, you would flip your right hand over or use your left hand. Again, I think that's dangerous. And the magnetic field from that current carrying wire is given by the equation B equals mu naught times the current over 2 pi times the radius. B is the magnetic field in Teslas, mu naught, 4 pi times 10 to the negative 7th Tesla meters per amp. That would be on the table of constants, just know where to look for that. I is current in amperes, R is the distance from the center of the wire measured in meters. Alright, let's take a look at this problem. A long straight wire conductor is placed below a compass as shown in the figure in the top view. So this picture right up here. When a large conventional current, that means the current is the direction of the protons. So you pretend that the protons are moving the way the current is shown. Now we know protons don't move, so that's why you got this kind of qualifying phrase, convention. We used to think protons moved, we know they don't anymore. We now know they don't. So current is pointing up, as shown here. When a large conventional current flows, as shown, which way will the north pole of the compass point? That's what the question is asking me. So what I need to do is figure out the direction of the magnetic field. because a compass will point in the direction of the magnetic field. So if I curl my fingers, put my thumb up in the direction of current, curl my fingers, I get that it goes around, back behind the wire, and comes out on top facing to the right. So that right facing arrow is on the top. Compasses point the way magnetic field would point, so the compass will point this way, which is to the east. Two things I should point out. The options remain undeflected or have its polarity reversed. A, remain undeflected, means that it should just point the way it was pointing in the first place. Not necessarily north, just before you put it down. So that would mean you're saying there's no magnetic field there. Have its polarity reversed means that the magnet would change its north and south end, and you can't do that by simply placing a wire under it. It's not something we talked about. It's more just a fancy worded answer to see if people are paying attention. So that would be like the clearly wrong answer. Alright, moving on. Alright, next up, two long straight parallel wires in the plane of the page carry equal currents I in the same direction, as shown above. Which of the following correctly describes the forces acting on the wires and the resultant magnetic field at points along the dotted line midway between the wires? Okay, let's do it one at a time. I remember from one of the past videos that parallel wires will either attract each other or repel each other. It won't be that one attracts and one repels. It won't work that way. And that's also Newton's third law. If one thing's pulling, the other thing has to pull. Newton's third law says forces equal in opposite directions. So if one is attracting, so is the other. So I just need to figure out if one wire attracts the other. I'm going to focus first on the bottom wire. I know this bottom wire, according to right-hand rule number 2, if I point my thumb to the right, I curl my fingers, that when I get to wire number 2, so I'll do this. This is wire number 1, wire number 2. When I get to wire number 2, if I curl my fingers around, the magnetic field from wire number 1, so B from 1 at where wire number 2 is at, will be pointing out of the page. You just curl your fingers until you get to the place where that second wire is. Your fingers are pointing straight at your nose, out of the page. Okay, so now let's figure out what the force, so I'm going to look for the force on wire 2 from wire 1. It's a long subscript. So if I've got my current to the right, my index finger points to the right, magnetic field out of the page. Again, when I do current to the right, magnetic field out of the page, I get that that force is down. That means that wire 1 attracts wire 2. Therefore, Newton's third law, wire 2 must attract wire 1. So I'll get rid of all the answers that don't say the wires attract. Now I need to know the field at the midpoint. Let's check this. The field from wire 1, if I curl my fingers, at the midpoint, pointed out of the page. Field from wire 2, we point into the page. And since that's right in the middle, if you think about B equals mu naught I over 2 pi r, they'll have the same r, mu naught pi will be the same, so it's just the i's that matter, and they both have the same current I. So the strength of the field will be the same, they'll be in opposite directions, therefore the total field will be 0. Alright, there's right-hand rule number 3, which is really just the opposite of right-hand rule number 2. If you have a loop of wire with a current running through it, so a circle of wire, you curl your fingers in the direction of the current, and the magnetic field points the way your thumb points. This picture, it's actually a little hard for me to tell which side is meant as the front of the wire. I think this is the front of the wire based on the magnetic field. That picture threw me off at first. So I curl my fingers in the direction of that current, and I get a magnetic field pointing out that way. Which means that in the magnet this creates, this will be the north end, and this will be the south end. Because magnetic fields point away from north and towards south. If it works for one loop of wire, it'll work for a whole bunch put together, which is this question. The magnetic field lines passing through point P, which is right there, inside the solenoid, is directed. Okay, so if I take my fingers and curl them in the direction of the current, I get that my thumb is pointing out this way, which means the magnetic field, it's kind of hard to draw, you need like a 3-dimensional piece of paper, come in like that. So upward to the top of the page. Yep. Alright, finally we've got flux. Flux is basically the number of B field lines passing through a loop of wire. And you calculate it using the equation phi equals B times A. And if you've rotated the wire at some angle, you throw in a cosine theta. But I have yet to see an APB exam question that is that mean. So phi equals BA is a pretty worthy guess. The only thing is, if your loop is turned so that there are no lines going through it, like in picture 2 here, so you can see in picture 1 that there are clearly lines going into the page through that loop of wire. If you've got no lines passing through it, no field lines passing through it, that's zero flux. So to know you can rotate that loop of wire until it's parallel with the field, and then you've got no flux. Flux is measured in what are called Webers, WB, or Tesla meters squared, or if you're feeling particularly clever, volt seconds, but Webers are fine. Magnetic field measured in Tesla, area, and meters squared. We also, from flux, get to Lenz's law. Remember, nature hates changes in flux. Everything has inertia. We all resist change to some extent. So do loops of wire. And if you have the flux changing through a loop of wire, that wire will actually create a current to try to keep that flux the same. So an induced current will be produced in a direction to cancel the change in flux. Remember, Lenz's law is all about change. Sometimes you'll have those tricky ones where it's like a loop of wire is inside a magnetic field. What's the induced current? And if it's just sitting there in it, not moving, not changing, or even if it's moving through it, but the field is staying the same, then you don't get any induced current. You only get an induced current if the field through the wire is changing. Remember, it's all about change in flux. And the way we calculate the voltage from the induced current, so not the current itself, but the induced voltage, is E equals delta phi over delta T, or your initial flux minus your final flux minus your initial flux divided by the time it took for the change. EMF is a voltage. So once you've got this EMF, you can plug it into V equals IR if you're asked for the current. You just take what you get out of this and put it in for V. So we've got voltage measured in volts, flux measured in Webers, and time measured in seconds. For a rectangular loop of wire moving in or out of the B field with a speed V, and this is only as it goes into the field or comes out, not if it's moving inside the field, only if you've got like a field like so, and you have your rectangular loop either starting to come in or starting to leave. When it's in the middle of the field, nothing happens. But the formula for that, your EMF voltage is E equals BLV, where B is the magnetic field, V is the velocity, and L is the length of the loop that is entirely inside the field the whole time. So if you notice my picture, this side here, always in the field. Let me color code. This side here, always in the field. And then that same length in the field as you're coming out. The way I like to describe it, because this is Mr. Tarshis' review sheet, so the way I like to describe it, it's the perpendicular length. Sorry, I said that wrong. This is my, and draw a picture to explain it. I'm going to slow down. If this is my loop, and my velocity is that way, it is the length of the wire perpendicular to the velocity. Okay. The reason I corrected myself is I just said it's the perpendicular length, and that doesn't make any sense. It's the side perpendicular to the velocity. So if I've got the velocity this way, notice that side is perpendicular to the velocity. So I would use the length of this side, which would coincidentally be the same as this side. So E equals the magnetic field times the perpendicular length, length perpendicular to the velocity, times the velocity. Alright, let's try this question. A square loop of wire of a side 0.5 meters and resistance 10 to the negative 2 ohms is located in a uniform magnetic field of intensity 0.4 teslas directed out of the page as shown. The magnitude of the field is decreased to 0. So somehow we turn off that field at a constant rate in 2 seconds. So it took 2 seconds to decrease that. I'm going to write that down so I can look at it later. 2 seconds. As the field is decreased, what is the magnitude and direction of the current in the loop? Well, first I'm going to figure out the direction because that would be easiest. I start out with a field out of the page, and I turn that field off. My loop does not like that I'm turning off that out of the page field. So it will try to make its own induced field out of the page. So in blue I'm going to draw what the wire will make. It will make a field out of the page. So now to figure out the current, I'm going to point my finger in the direction of the magnetic field, my thumb in the direction of the magnetic field, so thumb out of the page, and my fingers curl counterclockwise. So my induced current would have to run this way, like so. And again, that's because I'm turning off the field that was pointing out of the page. It doesn't like that I'm taking away some of its out of the page, so it will create more out of the page field. Okay? So now I can eliminate anything that's not counterclockwise. Boom, boom, boom. Now I need the amount. Alright, so first my plan will be to get the voltage, and then from there I'll go to the current using V equals IR. Because remember, I can't go straight to induced current, I've got to go to voltage using E equals change in flux over change in time. Alright, so my flux goes to 0 from, alright, let's see, remember flux is BA. So, B, 0.4 Teslas, 0.4 Teslas times the area of that wire, 0.5 meters squared, because it's a square loop. So this would be, for my square loop, A would be the length squared, divided by, for a rectangle I just do length times width, divided by the time it took, 2 seconds. Alrighty, so I've got 0.5, simplify this a bit, which will turn in squared, which will turn into 0.25 meters squared. And then that's 0.4 Teslas. So 0.4 Teslas times 0.25 meters squared, 2 seconds, that'll turn into 0.4 times 0.25 will turn into 0.01 Webers divided by 2 seconds. Sorry, I made a mistake here. Hopefully you guys caught my math mistake. It wouldn't be 0.01 Webers, it would be 0.1 Weber divided by 2 seconds. 0.1 divided by 2, I get 0.05 volts. Right now I take that, like I said, and throw in my V equals IR. V equals IR, so I equals V over R. I just found my voltage, 0.05 volts, divided by my resistance, which is 10 to the negative 2 ohms. And thinking about how fractions work, if you got a 2 to the negative 2 on the bottom, that's the same as saying times 10 to the 2 on top. And I get 5 amps. So 5 amps counterclockwise. Boom shakalaka. Alright, the end. Call me if you need help. Ask questions.